Hello and welcome to our presentation on lateral and longitudinal vehicle dynamics at high speeds for autonomous vehicles. This team comprises of 10 authors, and the team is led by Tim Vanderwood and Sam Smith. Low to mid-speed autonomous driving has become the focus of many industry and academic studies. High-speed autonomous driving presents its own new challenges. As part of the Indy Autonomous Challenge, our objective is to simulate vehicle dynamics at high speeds to predict faster race lines and safer trajectories for competition. This project focuses on helping the Purdue West Point Indy Autonomous Challenge team by researching vehicle dynamics of a modified Dallara IL-15 race car racing at high speeds. Vehicle dynamics can be split into two different areas: longitudinal and lateral dynamics. Our group was separated into two teams to cover these topics, each team studying text and other resources to describe the basics of each concept. After having sufficient knowledge of these subjects, MATLAB was used to create rudimentary models of the vehicle. Further research was also done to explore more accurate models of the vehicle for future work. Longitudinal vehicle dynamics studies the dynamics of the vehicle that generates forward motion. Applications of this field include longitudinal forces that act on the vehicle and driveline dynamics. Important concepts related to driveline dynamics include the speed and torque of the vehicle's engine. A model was developed to predict the throttle percentage at a given vehicle speed and engine torque. Lateral vehicle dynamics studies the left and right motion of the vehicle. Applications of this field include steering, lane keeping, vehicle stability, and vehicle control. Concepts important to the lateral dynamics include tire slip, turning rates, and instant centers of rotation. A kinematic model was developed to simulate vehicle turning at low speeds. Both teams developed MATLAB programs to model the acceleration and steering angles of the Dallara IL-15 race car. The longitudinal model for the driveline dynamics of the vehicle requires an inputted speed and engine torque. The model then outputs the required throttle percentage to achieve the inputted values. The model uses nonlinear regression equations determined from the engine matrix to estimate the load percentage of the vehicle. The first graph shows how the engine torque changes in Newton meters as the speed of the engine increases in revolutions per minute. This graph was used to visualize the data from an engine matrix in order to develop a model that predicted throttle percentage with the given inputs. The lateral dynamics team started with a kinematic model of the vehicle. The MATLAB program inputs velocity, yaw rate, heading angle, and outputs the x and y velocity, slip angle, and steering angle. Using this model, the steering and slip angles can be found for constant velocities and varying radii of curvature. The second graph plots radius of curvature versus the steering and slip angles for different speeds. As you can see, the 50 miles per hour and 100 miles per hour graphs are exactly the same. This is because in our simplified model, the steering angle and the slip angle do not end up relating to the velocity in any way. This is due to multiple assumptions that make the model invalid for high speeds. In future work, we will create a model that is more valid for high speeds, and we'll see differences depending on the speed of the vehicle. Both sub-teams have plans to create more accurate models in future semesters. These models will consider high speeds and more lifelike racing conditions. The lateral dynamics team plans to create a dynamic model of the vehicle's lateral motion in the hope to more accurately model high speeds. The longitudinal dynamics team plans to improve the throttle percentage model by considering the output gear and the downforce acting on the vehicle. We would like to thank our faculty advisor, Dr. Ali El-Gamal, as well as Purdue graduate student and IAC member, Manuel Eduardo Mar Valencia, for their guidance and unwavering support through our project. Thank you for listening to our presentation.